Guys, let us start with the topic of heat and calorimetry. Now, under this topic, we are going to focus mainly on the calorimetry and to the continuation of what we learned, and we'll finish up on some calculation with respect to the syllabus. So I am going to be a little bit fast, not that fast as well, but I'm going to be showing you what is needed with respect to your syllabus about calorimetry. So to understand this concept, let's start with definition of calorimetry. And please don't forget to like and subscribe. And as well, share the channel for those who are also doing physics in schools and need one or two things to know. So let's start with the definition of calorimetry. Now, in physics, when we say calorimetry, I think I'm going, and just say it is just the aspect of physics that deals with the exchange of heat. Like I do say, we have to write some things down in physics, and that is why I'm here. I hope you can see me. So we say calorimetry. Not this. Let me pick a better stuff. Let's use a blue. Now, calorimetry is just, or let's say, is the process, and that is better, of heat exchange, between substances. So the process of heat exchange between substances is what we call calorimetry. And we have all studied before. So, we started from kinetic theory of gas. And after the kinetic theory of gas, we talk about the what we call temperature and its measurement. We talk about temperature and thermometry. Then now after that, we talk about the transfer, or we'll say modes of the transfer. Now we are on calorimetry. So basically, we have talked about the process under thermometry, that when we heat a substance, when a substance is being heated, when you heat a substance, let's just take an instance. When a substance is being heated, basically there are going to be two things. The first thing we notice is that there will be, we will say, a rise in temperature of that particular substance, which I always denote by what, delta T. I hope you still remember this. And there will be another important thing, what we call a change in phase. We've talked about this under thermometry, as I've talked about. Now, the change in phase can be in different ways, or can be explained in different ways. Now, the very first one we can talk about is there can be a change in phase when substance changes from solid to liquid. We say the substance has melted. We call that process melting. There's another process we call change in phase when we say substances has evaporate. So we call that evaporation. And the very last one is a change in phase whereby we say the substance has what? Has sublimate. Sublimation, which I believe in your chemistry class you have studied about. So calorimetry is just a process of heat exchange between substances. And when heat is applied to substances, first thing is what? There's going to be a change in temperature due to increase in thermal agitation or energy of random oscillation between solid substances, liquid or gaseous substances, which we've talked about on that thermometry, like I said. So here we say the change in temperature. Now we say when a substance is being heated, that means heat is supplied. The measurement of heat, we said heat is the measurement of what we defined it in the last class by saying heat is the measure of what we can say. We say the transfer of energy between substances. Now, the amount of heat which we measure in joule is written in terms of quantity of, we've talked about this before as well. We write as a delta Q. So now mathematically, I will be expressing the amount of heat as Q, which is measured in joules. Now, if an amount of heat delta Q is what is supplied to a substance, and there is a change in temperature and also a change in space, you can say this amount of heat has caused, then the mathematical interpretation now, the way we write in physics, everything is about formulas and interpretation of formula, which we need to always keep at the back of your mind. Very important. So we say the change in what the amount of heat that is supplied to this substance is bringing about the change in what? The change in temperature, which we write as theta T. That's the first interpretation we give to it. We can also say the amount of heat of a substance is also proportional to the mass of that substance. That is the initial mass of the substance, which we say is the measure of inertia. So directly by combination, mathematically, we can conclude that the amount of heat, which we now call Q, that is supplied to a particular substance, is now equals to MC change in what? Change in temperature. I write as dT. Most of you are used to writing change in temperature as the theta anyhow. So now the constant of proportionality we have introduced here is called the specific heat capacity of a substance. So this specific heat capacity of a substance is a constant of proportionality, which also depends on the change in temperature of the substance. But with respect to the scope of our syllabus, I am only going to be limiting what is needed in the syllabus and not talk about the relation or relationship between the specific capacity and the temperature of the substance. So students should keep that at the back of their mind. And the specific capacity also depends on what is a constant here, the way we have been told to treat it in our syllabus. But we need to know, excuse me, that the specific capacity also depends on what the change in temperature. Now, the new parameter we just come across, which we call the constant when it is being supplied to a substance, which raise what? The temperature and the mass of the substance. And the constant of variable we call specific capacity is now defined. We can just write that to keep a note for future use, which I know you have all studied in your junior classes. And the specific heat capacity, let me just write in a word, specific heat capacity, which we denote as C, is the amount of heat that is required to raise the temperature of unit mass. Unit means one. Unit mass of a substance by 1 Kelvin. For that, you can write 1 degree Celsius. So please note that now it is denoted by C. We say the amount of heat required to raise the temperature of a unit mass by 1 Kelvin. Now, from the formula I have given to you, if you go by that, I said Q is equals to MC change in temperature or MC change in theta, as the case may be. So the way I write it, I love writing it like this. You might be used to writing your own as a MC theta. It is still the same thing, my dear student. Now we say it is the amount of heat required to raise the temperature of a unit mass. Unit mass means when mass is 1, then when temperature by 1 Kelvin. If you substitute M is 1 and temperature change in temperature as 1, you can say Q is equals to what? C. I hope students understand it. Let me bring my highlighter by substituting from definition. Now we say the amount of heat. Now everybody knows we measure it in joules, which we are still going to talk about very soon. Now, my point here is that the unit of specific heat capacity is very important also because of conversion. Is measured in now mass. You can see we say heat, that is a quantity of heat is something as specific heat. That means we can say joule. And we can make C sort of formula. It's also allowed. By doing that directly, which you have studied in your junior classes, we can say C is equals to, we can say this is Q into bracket M, open bracket. You can say this is change in temperature can be T2 minus T1, which most importantly, most of you are used to theta 2 minus theta 1. So we are saying the same thing. My point is we can get the units as a joule per kilogram. I write per kilogram as this, then per Kelvin. You can say that joule per kilogram Kelvin. You can say that is also per Kelvin. Another way you can write it can be equals to, you can say joule per kilogram per degree Celsius, because I know many of us, we are used to all these things in junior classes and in CGS unit. It is also measured in calories per gram calories per gram per degree Celsius or degree Celsius. So anyhow you have it because of conversion scale, you should keep it in mind that the amount of heat required to raise the temperature of a substance or a unit mass of a substance by 1 Kelvin is called the specific heat capacity. Then from what we have actually bring out here, let me manage this slide just to complete all what I want to talk about. There are always a lot of things you talk about. That is one thing about physics. And that's why physics is so easy to understand, because all these things can be practicalized. Now, in sequence to what we've talked about, we can see the mathematical relationship between the specific heat capacity of a substance and the what? And the temperature and the amount of heat that is being supplied. Excuse me, guys. Now, from here, we can say, let's just skip down a note just for me to manage this space. I don't want to go to the next slide. So, in continuation, we can just manage this data. We can just write. I hope it will be okay here. I should shift my hand a little bit up. Maybe I should take a ruler. Okay, I think that will be better. Taking a ruler will be very, very good. Yes, sorry guys, we are just trying to bring out all what is required because of examiners. During exams, there are some things that when you see them directly, if your teacher has mentioned it during class, it should be very, very easy for you to recall. Now, as a matter of fact, now what I want to tell you here is that I want to quickly set a relationship between the specific heat capacity of a substance, the quantity of heat, and the mass with respect to temperature. Now we can just write for a note and to keep it at the back of our mind that for low specific heat, just keep a note for low specific heat, for low, I don't want to rush you guys, specific heat, that is a substance with low specific heat, as you can see here, for a low specific heat, you can say small amount of heat. That is, you can see from here, you can say in your mathematical interpretation, you say C is directly proportional to Q. So for a low specific, that means when the specific heat capacity is low, small amount of heat, that means the amount of heat is also low. Small amount of heat will cause a huge amount. Let's permit my English, or an increase, a large increase. Let me use that simple English. That will cause a large increase on temperature. So what I'm saying, my dear student, is that specific heat capacity is direct proportional to the quantity, but inverse proportional to temperature. We can also write in the same way. We can say for high specific heat, for high specific heat, high specific heat. I hope I am not writing on where you cannot see. I hope. Now, for high, when the specific heat is high, you expect what the large amount of heat also to be supplied because they are what direct proportional to each other. Large amount of heat. I was trying to manage space. Large amount of heat will result or will cause small increase in temperature. So we can keep it in mind that in fact, in physics or chemistry as well, we say non-metals they have high specific heat. Non-metal, they have high specific heat, non-metals, whereas metals do have low specific heat. So when there's a low specific heat, you are well, the quantity of it to be small, and there will be a very large increase in temperature. When there is high specific heat, you expect a large amount of it to be supplied, or you expect the change in temperature to be very, very low. These are questions you can see, non-numerical questions that comes in the exam directly. You can just understand from relationship you set on that list. Now, Before I move to the next slide, let us quickly define another important parameter, which I think is also important. I'm sorry I have to manage space, which we call its capacity of a substance. Its capacity. It is also known as thermal capacity. I will just manage, as we have not that it's not going to be a lengthy video, but we are going to talk about the most important thing. That is what we are going to focus on, and that is why I'm trying to manage your space right from the beginning. Now, the heat capacity of a substance from junior classes or earlier classes, you have defined it as the amount, is also called thermal capacity of a body. The capacity of a body or of a substance is the amount of heat. We can just write the amount of heat, required to raise the temperature, I will use abbreviation of unit mass of a body. Unit mass of a body. Continuation is here by 1 Kelvin. 1 Kelvin is called its capacity of a body. So my dear student, the only important thing I would want you to keep in mind that its capacity, which is just what I will highlight, is equals to the mass of the body multiplied by specific heat capacity. I'll write as SHC. So generally we say it's equals to what? MC. So this is the interpretation we have talked about. I believe most of you have studied about this in early classes. So, and this is how we use this in physics. So keep it in mind. We say the quantity of heat is given as MC change in temperature, which most of you are used to saying MC theta 2 minus theta 1. Not bad, very correct. And its capacity of a body is defined. Then we can also talk about its SI unit. Thank God I didn't forget that, because SI unit is important. It's just like trying to make mass times, you can see the formula here, just cut out what? The mass. So you are going to have what? Joule per Kelvin. So the SI unit can be in what? Joule per Kelvin. You can also write it as a joule per degree Celsius, or anyhow we want to write it, or in CGS unit as calories. Or calories, or you say calories per degree Celsius. So guys, this is all what you need to know as an introductory part to understanding the concept of calorimetry. Here on this slide, we talk about definition of calorimetry, and we say it's just the process of heat exchange. That when substance is heated, we expect two things to happen. There will be a rise in temperature due to thermal agitation and random oscillation of bodies. And there is also going to be a change in space, which can be melt and evaporate, and it can sublimate. All these are physical processes we've talked about in chemistry. So we say the amount of it that is supplied is equal to MC change in temperature. And this brings us to another constant we call specific heat capacity. On the scope of our syllabus, I take it as a constant. It depends on temperature of a substance, but it is not within the scope of syllabus. That is why I'm not going to talk about it. And we talk about interpretation of specific heat capacity with respect to what the relation with the amount of heat supply and the effect on temperature. We say metals generally has low specific heat, and non-metals do have but high specific. And in summary, generally, I also talked about heat capacity. I said note is always mass multiplied by its specific capacity. So in this, we move to the next slide, where we are going to face about what we are supposed to face and see what is next under the slide. I hope students are getting this, and I hope you can see my camera. Like I said, my camera has always been issues in recent time, but all the same, I'm still working on it. Don't worry about it. It will somewhat get itself fixed. Now, the next concept we have to talk about, according to the slide, is the water equivalent of a substance. Wow. Now, in physics, when we talk about water equivalent of a substance, let's keep down a note as usual. You can say it is the amount of water. Let me just write, guys. The amount of water, I'm just writing for the sake. I will break it down. Don't worry. It's very easy to break things now. If you know it's the amount of water we say the amount of water there that has the amount of water that has the same specific heat as that of a substance. The amount of water that has the same specific heat as that of a substance is tagged as what we call the water equivalent of a substance. Now, to understand this, I've only written this in grammar form. I want to write it in a form in which you are supposed to know, which is understanding it in terms of what? Drawing. Now, let me just show you something now. When we say it has the same specific heat, or basically we say the same heat capacity. Sorry about that. Not the same heat capacity. The specific heat capacity is MC. So note that. Now, the same heat capacity as that of the substance. So now, for example, let's just take an instance. We have a body and we have to draw. Let's just take an oval shape. Let's say we have a body, just like that. This body is having a mass of m, and it's just a body. As usual, it's having, let's say the mass of this body, I will take the mass of the body as mb, and the specific capacity of the body, I'll take it as CB. So the body has a mass of MB and specific capacity of CB. An amount of heat is what supplied to it. The amount of it, I told you I'll be writing it as delta Q as we move forward. And because of it, this will raise the temperature of the body by delta T, that is T2 minus T1. We say T2 minus T1. Now, the water equivalent, I'm going to draw a picture. Okay, let's see if I can see that stuff. All right, let's just draw something. Not necessarily smooth, just to manage it, guys. So inside this one, this is filled with water to a certain level. So, and the same thing, let's say the mass of water was MW, the specific amount of water is CW. Then the same quantity of heat that was supplied to this was also supplied to this. Are you there? So, and this quantity of heat also rise to increase the temperature of this by also what? Delta T. So we now say if the same quantity of heat that is supplied to the body and raise the temperature of the body by delta T is also supplied to water and also raise the quantity of water by what? By delta T. So by symmetry, we can now say, if you don't understand any terms, I will always break it down. I am not rushing. Though I say I'll be a little bit fast, but I'm trying to break everything down. So now we now say the amount of heat capacity. What is heat capacity? In the previous slide, we say MC. So the amount of heat capacity of this one is mass of the body times specific heat capacity of this body is now equal to the heat capacity of this mass of the water. I hope you understand this. Multiplied by the specific capacity of the water. So we now say the water equivalent of this substance, which is M of water, is now equals to the mass of body, then specific capacity of body divided by the specific capacity of water. This type of relationship we have set here, my dear student, is now called the water equivalence of a substance. Most numerical and A-level physics for JUPEP students and IGMB students, you set up a kind of relationship that's what a body is having the same amount of the same amount of heat capacity, and when that about the amount of water which have the mass of water which has the same heat capacity as that of the body is now called the water equivalent of a substance. And sometimes you might be asked to define, and that is why definition is always very important. So I hope students understand this. And this is the definition and interpretation we give towards the water equivalent of a substance, which I think I need to talk about. So guys, I will move to the next slide. I hope you can understand it's not that lengthy. It's a short stuff, and that is what we're talking about. Now, the next one, my dear student, is that this is where we have to talk about some things. Mechanical equivalence of heat. Now, when we talk about mechanical equivalence of heat, I think I need to go back in history a little bit for you guys to actually understand this very well. So I'm trying to look at the camera because the camera has been giving issues. I said it in the last videos recently, but I believe we can still see the camera. So if that is the case, we can say here that now about the mechanical equivalent of heat, let me just go back a little bit in history and get about the 17th century. So let's put a look. Now, there is a man called, I know you guys have heard about, maybe not sure, in 1842 to be precise. There's a man called J. Mayor. His name is J. Mayor. He gave us a particular law and he said, eat and walk. Let me just write it. Eat and walk. Just listen. Are equivalent. Are equivalent to each other. So J. Mayer in 1842 said eat and work are equivalent to each other. That is, eat is the same thing as work. Then in 1943, the one you guys know very well, which you call joules. Now, joules, which is the unit of quantity of heat. Now, joules now came to what says that well, the relation is set, let me just write with another ink. Now, Joe said what? Mayor said eat and work are equivalent to each other. In fact, he said they can be converted. They can be what? They can be interconverted. They can be interconverted. That is, you can convert it to work and work to it. We've done work, energy, and power. For those that are just joining us, you can watch all our video series one after the other to have a deep knowledge and understanding of physics concept. So then if you have any issues, you can always write a mail to us. You can see the mail, and as well, you can call us. The number is showing on the screen as I talk. Now, guys, in 1943, to be precise, I was trying to bring out something. Jones came and he was able to tell us that he was able to set the relation between work, was able to set the relation between work or eat and work and eat. So that was what he did. I don't know, this is not writing well for my liking. So he was able to set the relationship between work and eat. And how did he do that? He said 1 calories, let me write in red, 1 calories, when you say calorie, you're talking about it, of heat is equals to 4.187 joules of work. So this has always been the way we convert. When I told you the other time about the CGS unit, this is the way we convert. That is 1 calorie of heat is something as 4.2 joules of work. And this was how the issues of conservation of energy started, which we have studied in junior classes. Conservation of energy started under thermodynamics. We are going to talk about, which is the last video set. So now it will take me 2.5 or 3 hours. Conservation of energy, we know energies can be converted. Now we can convert it to work. So far they can be interconverted. So we say heat from what we've studied is MC, change in temperature. Work can be in any form. We have different type of energy and work. Work and energy can also be interchanged from knowledge of our work energy theorem, which we have studied before in our videos. Now, work can be in terms of anything. It can be, you can interconvert work and energy, and you know what that means. It can be in terms of energy, half mv squared. Relationship can be in any form. MC, change in theta, or change in temperature. I'm used to that, I'm sorry. Can also be equals to mgh. So this is what was said, and this is what most of you use very well in your numerical. MC, change in temperature, can also be equals to, you know what I mean? It can be equals to the power times time is energy. You say power times time, which is also energy, because we are talking about that. And you know, power formula can be in different form, which I know you have also studied in your junior classes. MC, change in temperature, can also be equals to power can be current times voltage. Power can be I square RT. Power can be V square over RT. All these are elementary stuff I believe we have all studied before. And if not, there is always a first time to everything. So the conversion of this particular stuff was first introduced by J. Mayer, and later Joules actually take after it and was able to give us an exact value from experiment. And this is what we use in conversion. And this is how we talk about what's the conversion. So the knowledge of this was now used experimentally in determining or to determine the specific capacity of a substance. Now, in order to determine the specific heat capacity of a substance, so experiment or methods or the methods used to determine the specific heat capacity of a substance. Our students should keep it in mind here that we have different methods. In junior classes, we talk about, I'll only limit myself to the scope of the syllabus. I'm always saying that. Now, the first method is called method of mixture, which I'm going to show the demonstration in this video. The second is called electrical method. Now, these two methods are used generally to calculate the specific capacity by taking into consideration the instrument we use to measure the amount of heat loss and heat gain by a substance is called calorimeter, which I believe, you know, we talk about thermometer, different type of thermometer. One thing we just need to keep at the back of our mind, which is one of the most important things, is that I said something now, a calorimeter is used. You can see calorimeter. And there are some property of calorimeter. This is the amount of heat loss and heat gain. It is used to determine the amount of heat loss or the quantity of heat. So now when we talk about calorimeter, let me just write the most important thing. The calorimeter we are going to use during this experiment must be well lagged. Well lagged. So a well lagged calorimeter must always be used. That is, it must prevent what, if not all the amount of heat loss, there must not be what, it must not be what, must not be lost to the surrounding. So, and how do we achieve that? It is by what? Lagging the calorimeter. Some people will say you put cotton wool. I know you've done this thing before. And under our topic of heat transfer, you understand the effect of what? Door surface. When I say door surface, you know, when I say door surface, we say black bodies. They are good absorbers, they are good emitter, but they are poor radiant. So the concept is also used in calorimetry when we are trying to prevent heat loss as a result of what to the surrounding. The calorimeter must be lagged. And when we say a lagged calorimeter, that means a calorimeter that avoids what? Heat loss to the surrounding. So I believe you've studied this before, and if not, that is why I'm trying to still break it down a little bit for you. Now, to understand this very well, let us just quickly look into simple simulation, which I think is going to help us in getting by the method of mixture. We should understand that during this experiment, we use our well-lagged calorimeter, not only calorimeter, we use a steer too. Steer, I hope the spelling is correct, to steer what? The what? When we miss the substance we want to calculate. We have all actually understand that the amount of heat that is being what generated in a substance is always MC change in temperature, which I always like as delta T. This is my own interpretation. You can write it as MC d theta, whatever you are used to in your junior classes. It doesn't change anything. Now, by and large, my dear students, by method of mixture, let me quickly show you a demonstration on how it is being done with a simulated distance from Pearson. So we just want to quickly look at this and let's quickly check it out. Now, guys, looking at how it is being done to calculate the specific capacity of the body, we focus on this formula. And for now, I want to calculate in terms of temperature, the final temperature of the mixture, and from that I can calculate specific capacity. I will take you through it from this simulation. So let's quickly look into this, my dear student. Now, let's start. Now, as you can see, so we are trying to show a simulation to explain the specific capacity of a substance. And on doing so, we want to actually bring in something that will make us. So let's quickly do a kind of experiment. I believe you guys can see. Now, from this experiment now, this is a beaker that is scaled on what? You can see on the thermometer. And this is a calorimeter, which also has a stirrer. And this calorimeter is well lapped. Now, what I want to do now is that the experiment here is just to show you the method of mixture is being carried out in the laboratory. So, guys, what we are going to do here is that we are going to choose a liquid. We all know, and I'm going to do what? No, I'm going to choose a solid. Now, I want to calculate the specific capacity of copper. And how do I do that? This is the method we use. Now, I'm choosing a solid. The solid I want to calculate that of copper. Now, I'll take mass of copper. You can see, I'm just trying to show you the copper mass. I can take the mass of copper to be 50 grams. All these are going to be monitored and recorded. Mass of copper. And mass of copper initially is 50 grams of copper. The temperature of copper should be very, very high. I'm taking temperature of copper initially is 200 degrees Celsius, as you can see, my dear student. So the specific capacity of copper is this, which normally we are going to do that in numericals very soon. Now, mass of copper was kk, as you can see. The temperature of copper is 200 degrees Celsius illustration. Now, liquid, we want to talk about liquid is always water. Please note that. The mass of water, just let's take small mass of water. Let's say the mass of water is also say mass of water to be 50 grams of water. The temperature of water, I'm just taking room temperature of water as 20 degrees Celsius. So students should be careful. You have to write all these things down. Mass of copper, initial temperature of copper, then mass of water, initial temperature of water, as you can see. So now, and specific capacity of water is 4.2, which we all know from numericals, which you guys are used to. I'm sorry I'm rushing, guys. Now, the next thing I'm going to do now is that now I'm going to mix this one with this one, then I'm going to stir it to get the final temperature of the mixture. Now, my dear students, always keep it in mind that when higher temperature substance is mixed with lower temperature substance, the one with higher temperature will lose it to the one with lower temperature. So its loss from what we just talked about, the conversion from J. Mayer and Jones, its loss by higher temperature is always gained by lower temperature. This is the methodology you use in your junior classes, which most of you do say you don't know. Now, 200 degrees Celsius is the initial mass of copper. Copper lost mass, and it will be gained by water. So you can say initial temperature of water, theta 1 is 20. Theta 2 is what? 200 degrees Celsius. And the final temperature, you can see this one is losing. So that is why we subtract this one from this. But this one is gaining. I hope you understand. This one is gaining, and when it's gained, that means it should be what? You understand? So it's the one gaining temperature. The final temperature will be higher than this. So note that. So now to get the final temperature, now we mix them together. And when we do that, as you can see, mixing it together now, yeah, I'm pouring this one directly into this. Then we close this. We are trying to get the final temperature of the mixture, which is also going to monitor. You can see it's continuous stirring, and we are going to avoid heat loss. Very important. So we wait until this actually finishes. As you can see, the temperature is still reading. Initial temperature was of copper was 200 degrees Celsius. Very good. Final temperature, initial temperature of liquid is 20 degrees Celsius. And the final temperature of the mixture is 35.17 degrees Celsius. So my dear student, as you can see, my point here is that what? Theta 1 initial temperature of water is 20. Theta 2 temperature of copper is 200. And theta 3 final temperature of the mixture is 35.17. You can see copper is losing heat, and it was gained by what? By the water. So this is the way we now set up relationship in what? In mathematical what? Relationship from the formula to get different parameters that we are looking for. So please always keep this at the back of your mind. This is just a simulation, and for you to understand it better, that is why we are trying to do this for you guys. So guys, this is just that's that about that. Now let's go back to our initial stuff for better understanding because we need it. So we are talking about okay, fine. I think we should have this. Sorry about that. So we have the camera has started with visual. I want you guys to see me very clearly. So now I hope it's better. So we say we are back. Now, from what we just watched now, I'm trying to check the camera if the camera is back to normalcy. Not yet. Just for you guys to speak clearly. Sorry about that. I don't like switching off camera when doing classes. So that you can actually see my gesticulation and demonstrations. That's the essence. Hopefully it should be back soon. Camera position is not. So I think it's still okay now. Maybe. Yes, I think a yes. Now, that's what we have studied now. You can see that is the methodology we use in calculating the specific capacity of a substance from here, you can now see directly. Let me just finish up everything here that the heat loss, just heat loss by copper is equals to the heat gain by water, by conservation of energy, which is mostly what we use in most of the calculation. I hope you guys understand that. So yeah, what we're saying now is that we now continue from there. We use the formula. I'm always checking the camera, sorry. So heat loss by copper, we know the formula of heat is always MC change in temperature must be equals to the MC also change in temperature. From here, we can now finalize because we know the way the temperature is moving. So the final temperature, that is MC. Now we say this is, let me just help you guys. Let me use the theta you are used to. Now the temperature of copper is this theta 2. It's losing temperature when it was missed. The final temperature is theta 3 is equals to the one that gain, which is water. MC, this is C of copper. This is C of water. And I write it as CW if you like. This is for copper. So we have a MC of water. Then here in this case, you can see this one is gaining it because this one is gaining it. The final temperature minus the initial temperature of water, which is theta 1. So this is the relationship we set for this type of questions, which you can use to solve a lot of numericals. So it is quite very easy to understand all these things when you know the process and the methodology. So guys, this is the relationship we said. The one that gains it and the one that loses it is always determined by the one that has the highest temperature. So always keep it at the back of your mind. By the law of what, according to Joule's relation between work and heat, you can actually set up anything experimental to get the specific capacity of any substance. So this is how we do it, and this is the methodology we follow. So guys, this is all about a kind of what we call the change in the heat of the substance due to the change in temperature, which we call specific heat, because there's a change in temperature of a substance, and because there's a change in temperature of a substance, there's going to change in the specific capacity of a substance. So that is that about that. So the amount of heat required to raise the temperature, we've talked about it, and so on and so forth. So guys, keep it in mind because in numericals we are going to be using all these applications to solve a lot of questions. So let's move to the next slide. Yes, about the next slide, we have phase transformation. Very good. Now, this is the second type of what heat. When we talk about heat, we talk about the amount of heat required, the heat required, the amount of heat that is required to raise the temperature of a substance. And there's another type of heat that is required to raise the mass of a substance without a change in temperature. The first one, we are changing the mass of a substance by the change in temperature. We call that specific heat. Now, to understand this second type of heat supply to a body that does not change in temperature, which we call latent in your junior classes, we need to understand what we call the phase transformation. So in phase transformation, I'm going to split that into two parts. Let me see if the camera is still very much on. But it's quite important you can see me so that you can see my demonstrations. So now, guys, let's start with the first one. So we are going to talk about phase transformation. The first one I'll talk about is solids to liquids. So phase transformation, I'm going to explain solid to liquids. Now, let's quickly talk about that in a nutshell. Now, we understand that before that when we eat a substance, when substances is being heated, we talk about it. When a solid substance is being heated, let me just make it more solid substance is what I'm putting into consideration. So when substance is being heated, we know because of or due to what? Thermal agitation. We've talked about this under thermometry. Thermal agitation, that is energy of agitation. That is energy of random motion between solid substances. We increase a bit. We've talked about the increases. And when thermal agitation increases, excuse me, we expect what something to also increase. That is that the temperature of that substance also what tends to what increase, which we've studied. Substances increases. Now, students should be careful about this. Now, in continuation, now we need to understand something. Now, we know that energy of random oscillation we call thermodynamic increases, and that's temperature of substance increases. Now, we also need to understand that when substance melt, when we define the phenomenon called melting, for you to understand very well, melting, that is the temperature at which solids changes to liquid. Now, to explain this thing very well and for you guys to understand it, we need to understand the process. Now, substance melts when it turns from solid to liquids. Now, that particular temperature at which that happens, we call what melting point. So when substance melts, that means it changes from solid to liquid. The temperature at which it happens is called the melting point. So please have that at the back of your mind. So whereby melting is defined as a process which works. Let me just write it for the sake of solid turns what? Liquids. When solid turns liquid, we say that substances are solid. Now let's explain the chemistry process or the physical process to understand. Now, solid substances, there is what we call a force about the melting point or melting process. Now, the force due to collision of solid substance, there is forces of attraction, energy, thermal agitation between solid substances. Now, the force they continue to what? Everything continue to fight. They collide with each other even at low velocity because they are solid substance. Your chemistry knowledge. Now, the force due to collision continue to increase as the temperature increases, as we try to increase the temperature. But there will be a point, that is where we are going to, there will be a point whereby this force that is due to what thermal agitation is equal when the force due to collision of solid substance, force due to collision is equal, or that is, I didn't put is, that is why you have to be watching me, is equal to the coercive force, the coercive force between, I'm using abbreviation, I told you, between particles of solids. So when this occurs, they are thermal agitation, energy of random oscillation, they are moving, there is collision between them. So, but there will be a point whereby the force that is responsible for collision is equal to the coercive force. You know what we call coercion, we've done that. Coercive force between particles of solid. So when this occurs, we say at this point now, the supply heat, another point, I just want to make it simple. Sorry guys. The supplied heat, the supplied heat, I mean the amount of heat, it was the heat that is what causing thermal agitation. The supply heat will start breaking bonds. There is a bond that is holding solid particle, they are solid in nature before. At the moment, the force due to regulation is the same thing as the cohesive force between molecules. They what? Then something will what? The heat that is now what? The heat that is now supplied will now start breaking them. They will now start changing. We start breaking bonds between the substance. I hope you are there, between the substance, full stop. So the temperature at which this happens, the temperature at which this happens is served to be the melting point. It's said to be the melting point of that substance. So now, the most important thing about this short article I'm trying to write is just for you guys to understand that when substances melt, you need to keep it at the back of your mind that the force due to collision is equal to the cohesive force. And when that occurs, that means during the process, as the body starts to melt, there is an equality between cohesive force and force of collision. And at this point, we say the temperature, because they are equal, the temperature is constant. Temperature is not changing because cohesive force is the same thing as force of collision. So during melting, temperature is what? Temperature is always constant during melting. This is one of the most important things in junior classes, whereby you are going to do small experiment on how to determine the melting point of naphthalene. So you are going to say that before melting, the temperature of substance, as you heat that substance, the temperature of that substance increases. I've done this on my chemistry channels. You can check it. You can always check that. So whereby there is a graph whereby we explain the relationship between how melting is being done and so on and so forth. We can quickly talk about that. It's very, very simple. When you try to plot a graph of, I just want to manage space, that's another thing. I don't want to be plotting graph that will take all my spaces here, but I don't have option. I just have to do it because of some of us that we are beginners, you understand? So we need a comprehensive understanding of all these stuffs. So let me just use this one. I'm plotting a graph of temperature against time. It's just a simple stuff. Temperature against the time. Temperature can be in Kelvin or degrees Celsius. Now, what we're saying is that as a substance now, before the substance melts, I'm talking about temperature. See, when I heat that substance, what we expect is what temperature of that substance will increase to a certain point. You can start from anywhere. Let me start from the front because I'm starting from the back, does not change anything. See, if I start here, the temperature is rising to a particular point when the metal was heated. So after it was heated, then when the force due to collision is equal to the cohesive force between the substances, what we notice, my dear students, is what at that particular process, when the substances start melting, you expect the temperature to be the same because of cohesive force is equals to the collision force, or the thermal agitation force. So this is during melting. You can see during melting, the temperature is constant. That is, temperature is constant. You can see it's a straight line. So after the substance has melted, which is what we have talked about in chemistry, like I said, and the temperature will continue to rise. So this is more like what you call cooling curve and melting of in junior classes. So you say this is the melting point of the substance. And at this point, you can see that the temperature is the same. So when substance melts or during melting, temperature of substance is always equal. And the reason is because cohesive force is the same thing as force due to collision. I hope students understand that. So we say this is rising, you can put arrow, this is uniform, and this is constant. So that is it. And this is the lab experiment you have performed in your junior classes. And if not, there's always a first time to everything in life. So guys, back to what we're saying. So under this in sequence, under this explanation, we now define another parameters we call latent heat of fusion. For you to understand, for latent heat of fusion. Now we say the amount is defined as, this is a simple definition, the amount of heat required, the amount of heat required to melt a substance, the amount of heat required to melt a substance of unit mass. Sorry about the writing, I'm trying to manage space. Of unit mass, the amount of heat required to melt a substance of unit mass is called what? Latent heat of fusion. So the amount of heat, that is Q, required to melt a substance is given as M times LF, whereby LF is called latent heat of fusion. If you make LF, so you can see the amount of heat required to melt a unit mass of a substance, or to change, you can, if you don't want to use melt, to change the unit mass of a substance from solids to liquid. So these are what you can keep at the back of your mind. Another important thing is which I think I can also talk about because of those doing WAEC and NECO, which is also very important, WAEC, NECO, and all those categories of exam. You should also know that when we say during merit, there are some things you should keep in mind because it's very, very, most students don't know, melting and solidification. Solidification is freezing. Melting, solid to liquid. Solidification is the other one. Now, remember, density we call rho is equals to mass over volume. I just want to chip in this for elementary students over volume. Now, you can see now, we can say if the mass is constant, we can say rho, which is density, is inversely proportional to volume. I hope students understand the relationship I said mathematically here. Now, what I just want to quickly chip in here is that you can see when the density of a substance increases, the volume decreases. Now, the key point you can just keep as a short note, my dear student, is that during melting, you should know. Most students don't know that. You should always keep it in mind because many times I do tell students, you just need to understand when volume increases, density increases, decreases, and vice versa, whereby the mass is constant. I take mass as constant, all right? K, constant K. Now, two things. When you think during melting, I'll just talk about melting because I'm talking about melting. Volume decreases, right? Volume decreases. And density increases. Very important point. So during freezing, just put this here. So we say during freezing or solidification, so that is freezing. Then I said it will be opposite, volume increases. I hope you can see, and density decreases. Arrow facing down means decreases. So in fact, that is the major reason whereby ice float on water. Keep that in mind. And that explains the reason whereby what ice float on water. These are practical illustration I believe you have learned before. And if not, you can always what learn it from me. So that is what I'm talking about. So ice float on water, and it is because of that. So keep that at the back of your mind. Very, very important. Another important thing, one last thing, there's always something to say. Another important thing I can also tell you here is that effect of impurities on melting. So impurities lowers melting point. So pressure and impurity lowers melting point. So these are things you can just keep at the back of your mind for the sake of what examination. So impurities lowers melting point, but not all substance, but most substance. Impurities lowers the melting point of the substance. All these are very important because of junior students that are still writing junior exams, that is O-level exams. These are things you need to know. In fact, an experiment which I've demonstrated before, I think I'll help you guys post in quick time. Maybe after we are through with all the topics, I will start posting those sorts of experiments I've done in the laboratory, which are my classroom during the time I do teaching classes. So I will show you the effect of an experiment we call regulation. It's a very bold regulation. I didn't say relegation. Regulation is an experiment that proves how what impurities lowers the metal. And most questions in UTM and stuff like that test you on all these shorty concepts. I hope you understand this, my dear students. So, guys, that is that about that. We just have to what? Just have to keep this at the back of our mind. So this is all about that, about the amount of heat, that is required to raise the unit mass of a substance is called to what to change this phase of a substance from solid to liquid is called the latent heat of fusion. So the change that does not what the change in the state of a substance without changing the temperature, basic way of defining, is called latent heat. So latent is called latent. So it can be of fusion, like I said, and phase transformation, which is the first one when solid turns to liquid, which we call fusion. I'll quickly talk about the last one, which we call what? The other one, which we call when substances change phases from what we call liquids to vapor. So let's quickly talk about that also because it's also very important. Still on that, because I just quickly bring out another slide because that slide has been filled up. So let's talk about the second phenomenon whereby we call what liquid. We are still on phase transformation, liquids to vapor. Now, when you say something happens from liquid to, you say it has vaporized, and some people call it evaporation, evaporation. Now, to understand this, we need to understand this in two ways. Now, evaporation takes place in two ways. That is one. I'll just let you know. Let me keep that also. I said evaporation. Hope I'm still showing. Yeah, very good. Evaporation takes place in two ways. Or you say vaporization takes place in two ways. If you evaporation and evaporation are actually the same thing. So we said evaporation takes place in two, or vaporization takes place in two ways. That should have been the English I use for understanding's sake. So it should be vaporization takes place in two ways. And I want to explain the concept of evaporation. The first way we call evaporation, and the second way we call boiling. Evaporation, which we say takes place at all temperature, at all temperature, and boiling, which we say takes place at a particular temperature. Say the maximum temperature of evaporation is equals to boiling. That is the way the teacher will have told you in your junior classes. Now, to understand this process, let me also do my usual bigger things and explain as usual. So let me explain as usual, and let's just take something not that big. It's considerably big. Now, let's say this particular substance is filled with water to a certain level. So there's a liquid here, just for understanding's sake, my dear student. Nothing more pretentious. So I hope we have getting all these things to understand more and to solve more numericals. You can check on our physics playlist videos where you see some numericals and some exam question, exam solution. You can also check our other channels to see more of numericals for you to always practice because it's very important. And you can join our masterclass programs on Telegram. And for more inquiries, you can just go through the number that is scrolling on your screen. So we are talking about liquids that is filled in a container as a result of what we've talked about. So now this liquid, as we increase the temperature of this liquid, let's just take it a very quick way. Now, some liquid are very close here, and we heat up this particular substance. We supply heat to it. And we know because of that, the molecules that are close to this particular point, due to thermal agitation, we start vibrating at different energy. They start vibrating and moving and moving and moving and moving and moving and moving and moving. Just like that, my dear students, nothing more pretentious. So they start moving, 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 moving. And as they start moving around, what you notice is what? Those ones that are above them. Now, these ones are moving around. They start moving and they will start trying to what? To find their way up of this container because they are being stressed and they start moving up, and those ones up start moving, there's thermal agitation as what we've talked about that occurs due to what? Increase in temperature. Now, a quick one for you to understand, we know that there is this is a liquid substance that starts moving, the temperature is increasing, they start moving, they move around. The ones that are here very close to where the heat is being supplied start moving up, and they are trying to they want to escape the surface of this liquid. Please listen. As they try, let me use a black, as they try to escape the surface of this liquid, there is what we call atmospheric pressure. Every material always under the influence of what? Atmospheric pressure, which I read as P atmospheric. So as this molecule tries to escape, they try to escape the surface of this liquid, and you can see because of increase in temperature, the atmospheric pressure here try to push them back, and that is the essence of why I want you guys to be seeing me so that you can actually understand what. So now they try to pull them back, as in push them back. Now they push them back into the container. So as they push them back into the container, then a particular layer will now be formed here. This particular layer, which we call a thin layer. I just want to make a thin layer for understanding sake, will be formed here. This thin layer is as a result of this is a thin layer. And because the atmospheric pressure is greater than the pressure that is being exerted at this particular point, so all those ones that are changing, that are supposed to vapor, all the vapor that want to escape the surface of this little container or whatever, the beaker, or whatever you call it, will push back by atmospheric pressure, and the vapor pressure will be set here. So which is a thin layer, we call the layer of vapor layer, vapor plane. So now, but as we continue to the process continue to move on, we continue to supply it, but there will be a particular time whereby you can see atmospheric pressure is bringing in its own is bringing all those molecules back. And because of that, those molecules here are now stretching themselves to form a thin layer. I hope you understand that. And because of that, what you expect here is that there will be a particular time whereby because of the energy that is increasing as there is an increase in thermal agitation and oxidation of these liquid substances, you expect some of them will still find their way to escape in form of vapor. So those ones that escape in form of vapor are said to be to have evaporated. So now we can say evaporation is occurring at what? Because what we at all temperature, whatever the temperature, as we continue to increase temperature, there's thermal agitation, molecules move up, atmospheric pressure pull them back in. When atmospheric pressure pull them back in, with time, there will be a particular time whereby some molecules of the liquids or the vapor of the liquid will escape, will be able to gather some energy that is greater than that of atmospheric pressure, and at that point we say the particular substance has evaporated. That is the chemistry explanation to that. Very simple. Before, when the molecules are being pulled back by atmospheric pressure, we say the vapor pressure is less than the atmospheric pressure. That is the condition. At that time, substances are yet to evaporate. But when the vapor pressure is now greater than what? The atmospheric pressure, we say what substance what will be evaporated. And you can see from liquid now they have now turned from now at this particular layer, they are still in liquid form because of atmospheric pressure. But the moment they start escaping, they have now turned from liquid to because they escape in form of vapor as a result of the heat. So this particular process whereby substances turns from liquid to vapor is called evaporation, which takes place at every temperature. And as a result of that, your teacher in junior class will also tell you that evaporation takes place at the surface of liquid. Yes, it happens there because it's at this surface of at this thin layer that they escape to the world. I mean, I hope you can see. So that is just some quick interpretation to what your teacher has told you in junior classes, which you're also going to use in your senior classes to understand other concepts. So keep it at the back of your mind. But there is another particular thing that happens here. As we continue to increase the heat, there will be a particular point, which you can note, whereby the atmospheric pressure is equal, the temperature of atmospheric pressure is equal to the what? To the vapor pressure, which I call VP. So the temperature at which this occur is called boiling point. The temperature at which this occur, my pen is not writing okay back, is called the boiling point of that substance. So the point we just need to understand is that boiling takes place at a particular temperature. That is temperature at which the atmospheric pressure is equal to vapor pressure. That is when boiling will occur. But evaporation takes place at what temperature, and it's only at the surface, whereby this involves the whole process of the liquid. Another thing is boiling is a noisy phenomenon because when water boils, you start hearing noise. Now, those are things which I believe you've studied in junior classes. So, in sequence to what we have defined, now we can also define another important parameters, which I think is also very important, which we call latent heat of vaporization. Latent heat of vaporization. So we can say the amount of heat, just the last one before we go to illustration side, amount of heat required to vaporize or to change the unit mass. It has a change to required to vaporize. I just like using vaporize, nothing more. Vaporize a liquid of unit mass. So it's called latent. It is denoted by LV, just like fusion we say LF, and it is given as Q is equals to MLV. So the SI unit is very easy to know. This is joule per kilogram. Please note that either fusion or vaporization, it is given as a joule per kilogram. So that's the SI unit, which is also very, very important for students to keep in mind. So be careful about this now, about heat calorimetry. We've talked about two things. Heat required to change a substance by a change in temperature, we call specific heat. And the heat required to change the mass of a substance without a change in temperature, we call latent heat, which can be in two ways. It can be fusion and it can be vaporization. So every heat means in what with a change in temperature, this one no change out, no temperature change. So please always keep that. That's the difference between specific heat and latent. So many times in numerical, we use that knowledge also to form what to understand. For example, if you say ice melt, when ice melts, during melting temperature is the same, you expect M times LF. When water boils, the quantity of it required is M times LV. So by conservation of energy, we can always use heat loss equals to heat gain. So after it has what vaporized or after it has melted, it can now increase the temperature. We know that one is when temperature is being increased is MC theta. So conservation of energy is what we use to solve numerical conversion of energy. Let me just write conversion of energy or conservation of energy. So it's what we use to solve most of the questions. The nature of the question will determine the nature of the interpretation we give to it. So like I just said, by practicing, you are always going to understand more. Another important thing is that most of the time they tell you that why is it that or the steam that is coming out from water, I get in when water, but the steam burn the skin more than what the hot water itself. It is just from what we have talked about. It is because of what the amount of temperature, because of latent heat of vaporization, the amount of it that is required to what to vaporize, to change from liquid to vapor in unit mass of a substance is high, because the temperature at that particular point, listen, we say it is the maximum evaporation. Listen now, our boiling is the maximum point of evaporation. Because boiling will occur. Boiling will start occurring immediately after what we have what particles have evaporate. But the temperature at which what evaporation, or when we say the temperature at which atmospheric pressure is equal to the vapor pressure, which is the thin layer on the surface, that is the temperature at which water starts boiling, or any liquids, as the case may be. So keep it at the back of your mind. So if we talk about why vapor burns than the boiling water itself. Why does it burn? It is because of what latent heat, because it's the heat required to vaporize a unit mass of a substance without rise its temperature occurs at the surface, and because of that, what do you expect? You expect what you expect it, because evaporation is the maximum of boiling. Sorry about that. You have to keep that in mind. So that is why it burns the skin more than what the boiling water itself. You can see evaporation is max, is on the top, whereby boiling is taking place within the layers of the leaf. So please keep this in mind, and let us start the illustration slide. So let's quickly do illustration slide and see what we can do. Like I do say, my dear students, on illustration slide, I will only give you the light on how to solve the question. Your own is to solve the question and send the answer on the comment box, and that is how to know if you're actually following the class. So let's do this, guys. We have the first process. 200 grams of water at 90 degrees Celsius is mixed with 100 grams of water at 30 degrees Celsius. You can see 90 degrees Celsius is the point temperature. It's mixed with water, just like the experiment we did. So very easy. What is the final temperature? Very simple. So we can say heat lost by water is equals to heat gained by water, because it's the same water. One is hot water and one is not. So heat loss is equals to heat gain. Well, both of them are hot water, but one is hotter than the other. Heat loss is equals to heat gain. From conservation, we've talked about that. So heat loss is always MC change in theta. The one that loses it is the one that has high temperature. That is 90 minus the final temperature. That is we can call that the theta 3, just like what we did. So the one that gained it is the 100 gram of water, MC. So the final temperature is greater than that one, minus that. So I think they have the same specific heat because it's water. C gets cancelled out. What are the masses? The first one is 200 is equals to, we have 90 minus theta 3. Or let's just write X if you have issues with theta 3. What's the second mass? 100 theta 3 minus 30. So you can finish this, so I should finish for you. Divide both sides by 100. This is 2 into brackets 90 minus 1930 as X for you to be able to solve, because I know student very well. 100 gets cancelled out. This is X minus 30. So from what you know, 2 times 90 is 180 minus 2x is equals to X minus 30. X, which is theta 3. So directly you can finish here. 180 plus 30 is 210 is equals to X plus 2x. X plus 2x are 3x. 210 is equals to 3x. So X can be equals to 210 divided by 3, which is 70 degrees Celsius. So I think that is correct. And that is the right answer to that question. So that's that, guys. The second question is a calorimeter of thermal capacity. Remember 80 joule. Thermal capacity is the same thing as heat capacity. These are things we've studied in concept. Now, heat capacity is thermal capacity. From there, we can take it that contain 20 grams of water at 100. This is the mass of water. Keep that temperature, very important. Is added so that the final temperature of the setup is, we can say this is final temperature, which is theta 3. So fine. What is now the question? The calorimeter of thermal capacity of this, we have at 100 is added to, so that the final temperature of the setup is 50 degrees Celsius. So the amount of water that is added is dash. I think this question is not complete, but we can do it. We can say heat lost by calorimeter, because it's the one that has the highest amount of heat. we can say heat loss by calorimeter is equals to heat gain by calorimeter and the heat gain by water. This is more or less like the water equivalent of heat that we talked about in concept class. So you can just use the concept to solve this. This one is MC. MC is already given as its capacity is MC. And you have the temperature changes, which is the most important. That's why I said the question is not complete. There should be one more temperature that is needed to be given, and I don't even know why it is not here. So then the heat gain here will be, this is theta 3. This one is losing heat, just like what we talked about. You can see, which was not given. So we should know the temperature of this one. So if we say 100 minus 50, which is the first one, the amount of initial temperature, continuing about at 100, the final temperature is 50, that's 100 minus 50 here. Just following what I did there, guys, is equals to the heat gain by calorimeter. Now, in this case, now, I have MC. In this case, calorimeter is now gaining, that is, there should be a reduce in temperature, which should be given 50 minus MA. There's an omission. That is the issues with student preparing slides for us. So 50 minus, there should be a particular temperature. So I think there is an omission, and I cannot be correcting anything unless I just, the final temperature of setup is 50, the amount of water added. So you know I need the amount of water that is added. So 50 minus the particular temperature, I don't know, which should be given, then plus the heat gain by the water, which is the mass of water, MC, the same thing, that is a 50 minus X. So it's very simple to know. Now this is 20. Then the specific capacity, the calorimeter or whatever, will be given. So in this case, mass MC is 80. You can just substitute. This is times 50 times 50 times 50 times 50 is now equals to, you can see what you're looking for, mass of calorimeter. In fact, specific capacity of calorimeter, we don't even know. So the mass of water was given here, it's given by this one. Okay, MC of this one is also given. Sorry about that. This is MC was given to be 80 into bracket 50 minus X plus M that you are looking for times 4.18 into bracket 50 minus X. So what I'm saying now, guys, is that there's an omission in this question. The temperature when this thing was what? You can see 20 grams of water at 100 is added, so that I find the value of the setup is 50 degrees Celsius. The amount of water added. So there's a change in that there should be 3 temperature. Calorimeter of thermal capacity of this contain 20 grams of water at 100 degrees Celsius is added to the final temperature of the setup. Is added to, so that the final value of setup is, that's theta 3. Then there should be another temperature. There are 3 temperature now, theta 2, which is this one. Then the final temperature, theta 3. Then there should be equals to what? You have the initial temperature of water. So there should be the initial temperature of water should be given. So we can take it as 25 degrees Celsius. So which would be the value of your S here to solve for the mass of water. So this is the relationship you set for the second question to get the right answer. So that's that, and that's that. So the next one, what's best explain why a person suffers more severe burn when his skin is exposed to steam when boiling water is poured onto the skin. I talked about this, and I was able to explain to you what is called latent heat of vaporization. So if you watch the concept video, this should not be a problem. I don't even know the question is being said by the boy that is preparing the slide. So that's that. Then about this one, I think this is calculate the quantity of heat required to melt 4 kilograms of ice to raise the temperature of water from 50 degrees. See, 4 kilograms of ice. When ice melts, that is latent heat of fusion, MLF. Then you are raising the temperature, that is MC theta. Help me understand. That will be the total quantity of heat, because ice melts without a change in temperature. Quantity of it is MLF. ice, when the temperature is raised, that is MC change in theta. So what you need to do is just substitute. The mass is 4. Everybody can finish this. Then you tell me the answer. So guys, this is where I'm going to stop. Don't forget to like and subscribe and share our video content to your friends. And don't forget as well to click on the notification button. See you soon in the last video of it, which is thermodynamics, or what you need to know. I should be able to do that in 2.5 hours as I promised. So I will try as much as possible to prepare the slide, or ask the student to prepare the slide so that we can actually have the run of the class. So guys, on it, we are almost done before we start waves and other things. So guys, see you soon. Bye for now.